Still don't know who did it. I'm still fishing.
It's hilarious.
As trolling efforts go.
Yeah.
Yeah, they did screw up a little bit. They never actually bothered to like induce a termination check. Like, so the fan out of the tree that it uses in its little Markov like tree generator isn't necessarily set up so that it decays towards 1, right? So that this doesn't actually necessarily produce a type that terminates. It's stochastic whether or not it will terminate. I don't know the odds.
It's a feature.
Yeah, it may be a feature.
The injection sample.
Yeah, there you go.
Isn't that a theoretical thing, that Haskell's type system is not closed, so it's not guaranteed to terminate?
But, well, it's whether you add undecidable instances and all that kind of stuff. So, with no extensions, it'll terminate. With all the extensions turned on,
Okay.
that's about the way. All right. So how are we? We're all set up.
Actually, the name of the extension has the word undecidable in it. Odds are good.
The word undecidable, yeah, undecidable instances, undecidable
Or
superclasses
unsafe.
can both blow you off.
I've always loved that about Haskell.
Yeah.
The honest naming of the dangerous libraries, unsafe, undecidable.
We're adding control.lens.unsound as I speak. So there's a whole bunch of combinations that people want in lens that are just not sound in general. Like I want to take this lens and this other lens, and I happen to know touch disparate parts of the data type and stuff like that, you know. And we want to mash them together into a bigger lens. And so we've said no up until now, and we finally said fine, you can have them. We're going to put them in a module though. It's going to be control.lens.unsound, and it won't be exported by default. And then you have to explicitly ask for this. You know that you're loading the gun pointing at your foot. It's your own damn fault.
Which foot?
That's not deterministic. All right. So I suppose we should get started. So last month or so, I wound up giving a talk up at Scala World up in Penrith in the UK. So I gave an opening keynote for a Scala conference in Haskell. I figured that was a good follow-up to the keynote that I gave at a Haskell conference in C++. So I think I can close the loop somewhere here. Otherwise, there's a net debt. So look forward to a Scala talk at a C++ conference. And so the talk, I didn't tell them what I was going to talk about, and I didn't know what I was going to talk about until a couple of weeks beforehand. And I recently, this talk actually has long roots or old roots in Boston Haskell here. Like the second or third talk I ever gave at Boston Haskell was on some monoidal parsing stuff, some talks on monoids and reducers for big data sets, like reducing big data sets in parallel using monoids. That got me a job at S&P Global Market at the time, S&P Capital IQ, and sort of, is one of the reasons why Boston Haskell is still here, because we kept being here and doing these things. So I gave that talk, and then I gave another talk at the same time about how can I parse things in parallel. Okay, if I'm willing to change the grammar or look for grammars that are well behaved for this. And I kind of put the project to bed for several years until very recently, when now I'm at a company called Digital Asset. We do blockchain stuff in Haskell, and they asked me to take a look at some of the front end stuff that we do. And so we use a Visual Studio Code plugin. This is not our plugin, but for our programming language called DAML, the Digital Asset Modeling Language, which is a sort of smart contract language written in Haskell that runs on a sort of private blockchain. And we can talk about that offline. But the editor for that is an editor for a Haskell-like language. And that means that you kind of want things like IntelliSense and hovering and renaming and all that kind of stuff to work. But I would personally like it to be very robust. Okay, especially if you're going to have people who are not really Haskell experts writing this stuff. Okay, so I was on vacation and I spent a week writing a Visual Studio Code plugin myself, so I could get my head around the way the one that we have at work works. Okay, and so with Visual Studio Code, what they did was they implemented something they call the language server protocol, which is like if you've ever tried to write a programming language, one of the things you have to start facing is editor support. How do you provide highlighting and stuff for users, right? Everybody likes a different editor, and they're all working in different languages. So in general, this becomes sort of an n times m problem of filling out this stupid matrix of how do I support Vim for my thing? Oh, well, I make a file full of regexes that tells me, here's my syntax highlighting, my .vim file for my language. And then you make everybody go figure out how to bundle it or install it. Emacs, you ask John Wigley to do something, you know. Visual Studio Code has its own thing. There's a different recipe for every one of these boxes, or at least for every one of these columns. And then if you want to start trying to support your language well, then you really want to be able to get like context-sensitive renaming support. So when I go to rename food a bar, that I rename the symbol, I rename all the occurrences that are bound to that use site, not all of the occurrences of that string in the source file. Like I want this to be a smarter semantic rename, and those kind of things. And then making that port across these things is difficult. So what Visual Studio Code did, or actually I think maybe it was Adam that did it originally, and then Visual Studio Code stole it. I don't know. Huh? Who did the language server protocol first? Okay, whoever did it. Microsoft shipped one for TypeScript and for C# implementations of it, and then a bunch of other people started following suit. So there's an implementation of this for Haskell by a guy, Alan Zimmerman. And it's been coming along reasonably nicely. And what I was questioning was, like, how could I make small changes to my language to make this support more robust? How could I build a language such that I have sort of optimal language server experience? I don't have a language yet, but I'm going to build the language. What small tweaks could I make to the language now that would enable more robust editor support in the future? Okay, this is sort of the open question that I posed myself, because I have a few little toy language projects, and I'm willing to change them, especially if they're small, innocuous ways that don't really hurt the user, to make this experience more robust and quicker. Okay. So the language server protocol itself is this JSONRPC nonsense. So you send like a content header, which is the length of this thing in bytes or whatever, and then you send this over the wire and encode, decode, right? It's a UTF-8 string holding JSON. Yay. And it's got a pile of methods and stuff like that. Hey, look, I want to set up. I have been initialized. That's my reply. I want to shut down. Ask the editor to show a message or to pop up a dialog box. Request to get syntax highlighting or be notified about whether or not something like a file changed its contents and whatnot. Okay. So again, how can we design a language to allow robust editor support? So no computer science talk would be complete without a Dijkstra quote. So I'll take one out of context, because you can always do that with a Dijkstra quote. It usually means something. So he was talking at the time about the fact that there's a difference in the orientation of computer science on the different sides of the Atlantic Ocean, right? Now, at the time he was talking smack about the U.S. and corporate interests and like not having to understand like, oh yeah, that's just the IBM guy who doesn't know what he's talking about out there on the stage, and we all know that he's talking nonsense. Where it just didn't register for his Dutch brain. But taking this completely out of context, I can kind of talk to parsing approaches as being split by the Atlantic Ocean as well, which is that here on the US side, we have sort of the LR, GLR, LALR school, like the table-driven methods. Okay, they sort of bottom-up parsing. Whereas in the sort of European school, like you have Nicolas Vert and sort of Pascal recursive descent style of parser. So Parsec and all of these recursive descent parsing combinator libraries are sort of this school. Okay, so these are the two sort of major camps. You have the sort of Dragon Book on this side and the sort of Pascal style on the other, which the functional programming school has kind of gone the other, that side. There's happy and some tools over here, but nobody really wants to use them. But each of these is good at different things. The sort of LL school is very good about giving you information about the location at which you have an error. At this moment in time, what names have I seen so far? What's all the information that's in scope? Let me give you like IntelliSense kind of stuff about what should I tab complete here, right? The LL school is really good at the tab complete story. Like it's one of the things that you could do better with Parsec and the like, is we can supply you with, you can literally tab your way through every version of every legal syntactic expression or something. Whereas the Newt school is very good at giving you sort of error resumptions. Something went wrong, oh crap, I can keep shifting more stuff onto the stack until stuff starts reducing. Okay? And so I can recover from an error and give you more errors, which really mattered when things were offline punch tape land. But it still matters a little bit today. Like it would be nice to be able to see something past the first error in a file, which is something that we're generally very bad at in like C# style parsers, right? These recursive descent parsers, once you've got an error, recovery is a black art. It's not a science generally. Over here, it's still a black art. You have to put these error productions in your grammar. But sort of both of these things are problematic. So let's try and launch missiles at both sides. Maybe that's a current politics, not the best analogy.
No one's ever voted for him.
Okay. So what I'm going to do is I'm going to show that we can try and parse sort of like, how many people here watch Silicon Valley or whatever? I can do middle out. Okay? I don't want to necessarily start from the left and look for the rightmost parse, or start from the left and look for the leftmost parse. I want to start in the middle and look for stuff. Okay? So let's do middle out parsing of parentheses. Is that, let me bring this around. Get it. Come back.
People in the back see the cursor?
Huh?
Okay.
Let me get out of full screen. I just want to bring it up so that it's not at the bottom of the screen.
He's over 40, so he's sympathetic.
There you go. Yes, I'm over 40, so I am sympathetic. There. So, let's say that you had any soup of parentheses that you wanted. Okay? If you removed all the ones that were facing inward, you'd be left with a number of parentheses facing out, right? If you removed all the pairs that match up, you'd be left with some number of unmatched parens facing out in each direction, right? So what I can do is I can just summarize that by counting them. So far so good? And then what I want to do is I want a monoid for these. So given two sets of parens that match up like this, or cancel off the middle. So what is the unit for my monoid? I have no parens of either sort, right? So here we have some A parens going this way, some B parens going this way, some C parens going this way, and some D parens going that way, right? So if there's fewer B's than C's, then the C's overwhelm and become A's. They cancel out all the B's. And we have, otherwise, that looks symmetric. All right, that appeals to my sense of symmetry. And then we can describe how to parse. I want to parse an opening paren as an opening paren. And I want to parse a closing paren as a closing paren. Parse everything else as, for neatness sake. And then we can answer whether or not a string is balanced by saying, hey, look, fold map over this with the parse function and see if it's the empty string, or the no parens. Okay? Now, if I didn't make an idiot out of myself, I should be able to say, hey, look, is this string balanced? Yes. Is this No? Yes? No. Congratulations, we can now parse lists in parallel. You have to put some identifiers in there, but you know, everybody knows they don't really matter. Okay, so this is our first example of something I'm going to call a Dyke language. Okay, so there's another Dutch guy who, way back in the day, came up with these things for parsing what are now called visibly, like they're generators for these things called visibly pushed languages. Okay, now you can generalize that. Like the thing that I parsed there, and the reason I used B, is because the thing I showed you is something called the bicyclic semigroup. Okay, it's actually a monoid, not a semigroup, but they call it a semigroup because I don't know if monoids were a term, but they were using it. But so we can generalize it. So instead of having just a single type of paren, if I had multiple types of parens, I would have to have a sequence of closing context and a sequence of opening context. And then I would pair them up and have to report errors. Right? That would be the general idea. So if I want to be able to match with matching not just parens with parens, but braces with braces and brackets with brackets, and my language is going to respect the fact that I don't have a paren paired with a bracket, I don't have a dangling paren anywhere in my grammar, which is a reasonable assumption about most programming languages, then what I could do is I could do this as sort of a parallel preprocess over almost anything that I want to parse. Okay? So now I want to move on to so what I'm doing here is starting to say, well, we might want to have a sequence of tokens between, so a closing context has a sequence of tokens that's at the beginning of it before the closing paren or whatever, the closing bracket, brace, whatever. The opening context should have a sequence of tokens after it. Then here we have a sequence of closings, which have tokens interspersed between them, a sequence of tokens in the middle, and then a sequence of openings facing that way. And then we have to mash all this together. Yeah, I can actually show the code and the implementation afterwards. It's a little bit more complicated than this, but this is the general sketch. So now we might think, oh, well, I can start handling my comments this way. I could look for multi-line comments, because in Haskell we support nested comments. And this is the problem. Nested comments are not a Dyke language, not in Haskell. And I can see that by, what is the meaning of this line? Huh? It's just a single line comment, right? Unless I'm in a multi-line comment. Now it's a string. Right? But if I'm in two, now it's a comment. Now it remains a comment again. So this pairs up with this, but then that quote is inside of a comment, so it doesn't mean anything, and so we resume parsing as a comment again. So we close one layer of nested comments, but then we open another one back up, and so you never come out of a comment. So in 0 or 2 or more levels of multi-line comments, this is nothing. In one level of multi-line comment, this is a string.
But also, does it open another level? Or
This reopens the level. If you put 2 of those in there, then it'd be a difference. Yeah.
It's quoted, so the quote doesn't.
No, the quote doesn't mean anything inside of a comment.
Okay.
So I just wanted to show that this sort of makes comment parsing in languages that support multiple levels of nested comments inherently problematic. It kind of requires a sort of necessarily left to right parse. Like you could say, well, we don't do this in practice, but there is a sort of idiom that people use in Haskell where they say something like, hey, look, I want this, and then I'll do something like that, and then I'll turn on or off this. Because in this setting, this is a single line comment, this is a single line comment. In this setting, this is a multi-line comment, and it ends itself. So I can turn on or off the contents of that thing just by putting in those 2 characters, right? So knowing the token stream for this middle actually is entirely dependent on the number of levels of comment nesting that I made. So screw it.
Does it help if single-line comments don't toggle multi-line comments?
Yeah, the problem here is that none of your editors tell you how to support any of that crap. right? Your editor just gives you what's your opening multi-line comment thing, what's your closing multi-line comment thing, what's your opening for single-line comments. And it doesn't have any idea how they interoperate, right? So I'm taking the incredibly brave step of removing multi-line comments from my language, and if I replace them with hash, no one expects them. All right. So if you take nothing else away from this talk, multi-line comments are evil. And now we can have a script line that tells me which program to run with it. All right. Okay. So now the next question is, so that fixed the comment problem, which was just shutting us down out of the gate. What I kind of want to be able to do is support everything that my editor wants in sort of polylog-ish time. Okay? So I want to support everything up to the renamer in my editor in log-ish, some log to the nth power, whatever n is. I don't know what it's going to be. It's not going to quite work out, unfortunately. There's a technical wibble. But I want it to be as fast as humanly possible for files that might actually be edited. Okay? And one of the things that I want to be able to support are, we're in a Haskell-like language, right? Or the kinds of languages that I'm interested in are Haskell-like languages. So I would like to be able to have references forward to types that occur later in the file. But these things get screwed up all the time in other programming languages. Oh look, I'm in the process of typing here. I've opened a curly brace. That's invalidated everything else in the rest of the file. Right? Because which brace does this brace match up with? Who knows? Right? So this is one of the places where the notion of an error production, of something like trying to resume and limp along again, but the moment you can start doing reductions again, where the LR school really shines, is because they can recover from some of these errors, right? And there's some crazy stuff for like trying to figure out where to magically insert a closing brace or something. But it's all rocket science and voodoo. And it's the intersection of people who are good at both that can do these things. So I'm just not interested in the sort of magic solutions here. And I want to be able to say, hey, look, if I'm hovering over a definition up here and I have a type from down here, I want to be able to show the type of the thing in the editor. I want that to be stable and robust, even in the presence of garbage. So how can I make an editor that is robust in the presence of nonsense? Okay? And so what I started to do before was we started to talk about these type languages where I've got these parens and braces and brackets and stuff like that. And saying, hey, look, these are a thing that my language will respect. Like, no matter what grammar I'm building, it will be built in such a way that it has balanced parentheses in it. That's a simple quotient of the language I want to work with. And that's not tying my hands too much in my language design, right? I don't know what my language is going to look like. I want to make as few commitments as I can to get the editor tooling support and such. But saying that you're going to have balanced parens and braces and brackets isn't terrible. I don't think anybody here would really dispute that that's a good thing. So one of the things that I like Haskell-like languages for is that we have layout. And layout is kind of like the type language in the sense that it gives me a good sense of what pairs up with what. Almost. I mean, there's some unfortunate problems with the way layout is implemented in Haskell. Okay? But layout, how many people here are not familiar with layout in Haskell? So anybody completely new to Haskell? All right. So in Haskell, are you familiar with Python?
Yes.
Okay, so the indentation in Python tells you when a definition ends, right? And they do it with a colon or something like that. They'll tell you where the block starts, right? Here we just have a set of keywords that give us the same kind of thing. After where, the indentation of the next keyword tells us where the layout block begins. And then everything that's indented to the same level as that keyword gets a sort of virtual semicolon inserted between it. And everything that, if it outdents, then it ends the where block or the let block or the of. But there's this really annoying rule buried in the Haskell language report, right there. And it says that if you ever get a parse error, layout stops. Okay? So if you're parsing through your program and it would introduce a parse error, what it does to try and recover is it tries to insert a virtual closing curly brace. Tries to end the current layout block. Okay? But this means that I can't parse layout as like a quotient over my grammar. I have to actually fully understand my grammar in order to be able to successfully parse layout. I need to know what is a parse error in the whole language in order to be able to parse layout at part. Yes?
Question. You were implementing your own language. Why didn't you just drop this rule?
Ah, congratulations. So if we drop this rule, and that's exactly what we're going to do, then a few things will cease to parse. But we're going to get some nice things out of it. So this is exactly the solution.
Okay.
Thank you for that lead-in. So in Haskell today, what I can do is I can put a paren around a do block. And then closing this paren is actually a parse error that then gets fixed by inserting a virtual curly brace. Okay? And then it says, oh, look, then I can compare the paren. Okay? So without that rule, we have to move to that encoding on the right-hand side. It's okay, it's just you have to be aware that you have to do it. The other one that would bite people in practice, and this is, I'm okay with it, biting people in practice, is let in. Let foo equals bar in bar, or something like that, right? This in is a parse error. You parse through this thing, I open up a layout block. Inside the layout block, I try and parse the declaration, foo equals bar. It goes to find the word in, goes, what the hell is that? Gives up, inserts a virtual curly brace, ends this statement, figures out that was well parsed, and then says, okay, fine, the let block's over in bar, we're good. Okay, so each of these things is parse, blow up, resume, right? And so these relied fundamentally on that awful rule. So fine, screw it, that rule's gone. Again, making the language up, I can do whatever the hell I want. Makes life easy. But it does mean this little curious syntactic quote.
And you're thinking that syntax if it's a one-liner. If you make it 2 lines.
If you make it 2 lines, even if you did do foo bar and then you like move to the next line with in, you'd be okay. If you outdated it far enough for in,
yeah,
it'd be okay. Yes.
Does in bar parse just on it by itself?
No, but it does after a let group of state let curly brace, bunch of stuff, closing curly brace in bar does parse.
Right. So when you insert the closing end of the line, essentially.
Yeah, the closing curly brace
Yeah.
basically closes this thing that got a virtual opening curly brace. It inserted a virtual closing curly brace, and now it parses.
Oh, okay.
It parses basically as that. So, while I'm playing around with this stuff, if I wanted to support some other things, I might be willing to tweak the rules of layout further. And one of the examples of something that I might want to parse is that like Chinese, Japanese, Korean fonts are all, they have very different widths than these sort of Western fonts, right? Like everything there is like the characters are twice as wide as our stuff. Because like, you know, we basically make everything twice as tall as it is wide, but that doesn't work for those fonts. Okay? And so in Unicode, trying to say that all my characters are the same width is really a losing game. So maybe what we should be doing is we should be saying, let's try and make it so that we can edit source code in a way that doesn't presuppose that every character has the same width. But what does this do to layout? It's just a question, right? One of the things that people do with layout is that they can write, layout can be dangled on a line. I can say, hey, look, foo equals do bar fast, right? Now the width of foo and do and equals affect the number of spaces I should use to make this thing go, okay? The other style that we use in Haskell is something called like a hanging do, where we go to this sort of style, right? Where we say, hey, look, foo equals do, and then we indent to the next line. And then we have some amount of white space. And now white space is paired up directly with white space. And I don't actually care about the width of these characters. If I renamed foo, this thing would still be stable. In the non-hanging do style, if I renamed foo, I might have to insert white space in the subsequent lines. So I want robust renaming support. Maybe what I should do is require hanging do. If I do it stylistically anyway. Screw everybody else. My language. And the other thing is that in Haskell, Haskell, what we do is we have this magic rule that says, hey, look, tab stops are exactly 8 spaces apart. But you don't need it, really. That's just saying that, like, we're requiring everyone to set something up in Vim or something like that they usually don't have set. It's just begging for problems. So what I can do is say this, that layout is actually determined by an exact sequence of whitespace characters. If you want space, space, tab, space as the indentation for your layout block, just do it consistently, and I don't care. Okay. It takes the sort of, what I get is a join semilattice for the prefixes of lines. Okay, so you give me, like previously it was a number of spaces or something like that, right? And I joined with min. Okay, and it has a cancel-if 0. It has a 0 which is 0 spaces, which annihilates everything. 0 times anything is 0. Okay. But it doesn't have a unit. It's not a monoid. There's no infinite number of spaces that I can join with another infinite amount of spaces to get the shorter of the 2 prefixes. Here, what I'm doing is I'm saying take the length of the longest common prefix between a white space characters between 2 strings, and that's my new one. Okay, this gives me a similar join semilattice, but now it's a partial order rather than total order. There's one extra case that I have to start thinking about when I start talking about how to do layout. Okay, but with that in hand, the trick here is that there's a monoid that I can use, just like I built a monoid for doing parens for doing layout. Okay, so I want to parse layout monoidally, and here I'm not going to write the whole thing out, but I'm going to sketch how it would look. So I'm looking at lines of text. So I broke my input up into lines. I want to like glue the lines together monoidally. Okay. So here what I have is like the Dyke language skeleton, like the set of tokens that I got for a line, as some kind of catenable list. These are awful. Okay, so what is this stuff? So I'm looking at a run of lines here. And what I have is a series of lines that are decreasing in indentation until I get to a peak. Like this one's like a little V shape. These are like closing contexts. These are like opening contexts. The opening contexts increase in indentation. This is logically considered one line. Because like there was no layout keyword here ending this line. So this is one line. So this could be bar, quaxware. This is still one line because as I glued this onto this line, it used the fact that the peak was out here to pull all this together. And then what I want is that each one of these, how to put this? When I go to glue 2 of these little V shapes together, there's a rule for how these things cancel out. Okay, so I have to have the notion of a block, which is like one statement or most of a statement. A run of blocks, which also has to have associated with it the result of having concatenated them, because I can't afford to concatenate them. And then an ascending sequence of things. So it's this weird set of closing contexts, run of things at the same depth, set of opening contexts, or set of runs of each of decreasing depth. Yes?
Sorry, I didn't follow. Why can't you afford to close to concatenate?
Because it might actually be every statement is at the exact same indentation level, and what I want to do is I don't want to pay for the number of lines in one step. I want to be log-ish, not linear. Okay. So what I do is I store a run as sort of like a run is not just a single Dyke language skeleton, but also a catenable sequence of Dyke language skeletons. Or rather, it's not just the catenable sequence of each individual block, but also the thing that I would get if I were to glue all these things together. So, like, let's say I have a run of lines of the same indentation: foo, bar, bass, right? The moment I see do here, I know that each one of these things is separately supposed to be parsed as a monad statement, a statement in a monad. Okay? But if instead I see, I don't know, clocks here, I know each one of these is actually arguments, and this is actually one longer sequence of tokens. So I can use this either as a capital type thing or as a type thing in its own right, depending on the two different contexts that it could possibly be used in. So do both. They're both O1. Yeah, so anyways, this is the crazy stuff that I have to think about in order to make this stuff go. But the layout stuff is really this sort of you can think of it as outdenting followed by indenting, where I manage runs of the same length by storing them both ways. And then these things can glue together, using the same kind of logic that makes the language skeleton go, except now a single closing context doesn't necessarily pair up with a single opening context. You might pair off against multiples. So it's a more generalized notion. So those are good? So, but now we have another problem. Like we've already kind of alluded to the fact that we're starting to pay too much to do things. So how can I, and the other thing here is I want all of this stuff to work even in the presence of garbage, right? When you have unbalanced parens, what I have is layout gives me a place to recover. Foo equals do, and then I have a leftover parens or something like that. I can start resume parsing at the next statement in the monad and syntactically resolve my problems. Okay? If I'm looking at the top level where block that is my module, I can move to the next definition because it's the next thing that's fully outdented. No matter what garbage you've got on the current line, I can resume parsing for the type signatures and whatnot. And so, how many people here have heard of crash-only development or crash-only software? Anybody come up with a few? That's some of the old terms. So it was a sort of notion of, whenever you put a graceful exit path in your application, so you have a shutdown command or something like that, all you do is you make sure that the crash path doesn't get tested very well. Right? It's an optimization, and in many ways it's a premature optimization. So if you want your recovery path to be tested well, maybe what you should do is only have a recovery path. Don't have a graceful exit, just shut down messily every time, and then you'll see what goes wrong. So here what I'm doing is a sort of crash-only parser development. I can't actually successfully build parse trees, because I don't know what my parse trees are going to look like. But I still want to be able to support everything in my renamer and all this other kind of stuff. I want as much of the tooling to work as possible, even in the broken cases, so I only have the broken cases right now. Okay? So I'm doing crash-only parser development. So let's move on to how I have to report errors to Visual Studio. So in Visual Studio, they take errors as like a position as a number of lines, and a number of columns given as a number of characters into the line, not, there's no tab stop rule, it's just a character's a character. And they figure out where to put the wibbles on the line. Okay? And I could make a monoid for these positions to represent like small changes. So I'll say like, if it's 0 lines, and these are like a relative shift in the number of columns. And so what we're doing here is if I go to glue something that's like an absolute line count followed by the 5th column or something in that, and I'm not changing the line that I'm in, then I'm just adding to the relative line position. That's the B plus D. On the other hand, here I don't care what column I was at because I'm overwriting it. So I add the lines and I clogger the column. Okay, so this gives a monoid, and I've written it this way rather than as 2 data constructors, one for like column and one for line or something like that, because this way it can be unpacked inside the data structure. But also because this is the exact data type that I have to send to Visual Studio Code. Now the problem with this is it's only a monoid. So I'm going to be doing a bunch of things that I want richer structure for. So I want something that actually has a group structure. So I'm going to choose the worst encoding of positions of all time. How many bytes are there since the beginning of the file? Or a number of actual UTF-16 code units, not even bytes. Okay? So these are not characters, like if you have surrogate pairs, like these are individual halves of a surrogate pair get counted as individual ones, right? And we've all like used some kind of JSON, something or other that says, hey, look, 538 bytes into your input JSON document. There is a problem. Go find it. And it is awful. You never want to use these things, right? But this has one nice property. It's a group. It's an abelian group. It's addition, right? So it's commutative, not just associative. And I have inverses. I can say, hey, look, I want to go 50 characters to the right. No, I want to go 50 characters to the left. Okay? So this gives me a group. So the mathematician in me is really happy. And the thing is I can convert between that to this in log time anyways. So if you give me a finger tree with the lines here summarized, whatever, I can move back and forth between the two representations in log time. So if my goal is polylog, right, I can do this and it doesn't take me out of the space. Okay? So far so good? So I'm going to work with this internally. All my errors are going to be locally relative to, like they start relative to the line, because I'm going to parse my lines independently. What I did was I got rid of multi-line comments, remember? When we got rid of multi-line comments, we made it so that I can always start my lexer in an unambiguous state at the beginning of every line. I can start lexing on the line. But if I build a set of lexemes on the line and I want to put positions in my lexemes, I have a problem. How do I report them to the user? How do I build syntax trees out of them? Right? Because they were at relative positions. When I go to glue them to another set of things that were relative positions, this whole thing becomes a mess. Okay? And let's say I want to report errors to the user. The errors occurred at different locations in my source file, and I need to be able to move them around as I make small edits in sublinear time. Okay? So I'm going to run into a bunch of problems here, which I'll try to address all at once. Okay? So here's our delta. Let's just start there. So let's say I have an error that has occurred at some delta in what I've seen. I saw it within this line, and I want to move this line occurred at this position inside of this larger file. So what I want to do is I want to have the notion of what's called a monoid action. In this case, a group action, because delta is a group. Okay? And what I want is that relocation by mempty, relocation by the simple no change, should be the identity function. And relocation by appending of two deltas, again, the sum of two deltas, should be relocate by one delta followed by relocate by the other delta. Okay? This is what a monoid action is. Rel is a monoid action with respect to delta. So delta acts on this set A, whatever data type A is. Okay? So here, like, my errors might be, at this position, there's a problem. And I should be able to relocate that by saying, hey, look, you give me a change of position, apply it to the original delta by just appending the two deltas. Now this works for position or for the delta that I just showed. Any monoidal delta, any semigroup delta, this works fine. Right? But here's the problem. How do I get back a list of errors? If I give you a list of errors, I can relocate a list of errors. I just fmap relocation over the list. But if I have n errors, that could take too long. I want to be able to relocate all n errors in sublinear time. So how can I make it so I can relocate a list of n things in O1 time?
Put the
Okay.
location trick in the location list. Put the location inside the list.
All right, let's do it. So we had that one. So what I can do is I'll bolt it into the const cell of the list. So const now knows the delta, and the delta will apply to both the head of the list and the tail of the list. So the act of unconsting will push the delta through. It will relocate the head and then relocate the tail, which just updates the delta. So unconst had to pay O1 to access that node anyways, so it can pay O1 to do the relocations. Okay? So I can relocate nil and get nil. I can relocate anything by 0 and get itself. And I can relocate by delta const of something and just append the two things. So this is clearly O1. And unconst is clearly remains O1, assuming that relocation of elements is O1. So all we did was buried the asymptotics at the access time. Okay, we just moved it around. So now I can relocate lists in constant time. But now appending lists is expensive because we started with a normal list. But Okazaki has a whole book on how to make beautiful data structures that like give you O1 append and have O1 access to the list, or log time access to the elements and stuff like that, right? So we can just basically use the same trick on anything out of Okasaki, just by shoving the delta in the data constructors, and then moving it down through the tree lazily, like as needed. Whenever you go to access something, it just moves through. So one way to do this would be to just make a smart constructor. Here's consts for my list, such that if I go to pattern match with the const AAs, and I have a const constructor with a delta in it, I apply the relocation to the head and the tail of the list before I see them. That gives me the A and the A's that I see. And if I go to construct with it, it constructs with the 0 delta. Okay? So if I only ever used const prime and nil, you would never know that I was slowly relocating your terms. Right? You could work with this as if it was a list, you just wouldn't know. Okay? And here we compare them as if they've been unconst using this machinery. And we show them using the same machinery. So you can't see the pile of deltas that we're accumulating. But what we're doing is we're sort of mashing the deltas together as we go. If you like your category theory, this is like applying CODA data to the data constructor, and we're looking at just the image of delta as the kind of functions that we have, because those functions get mashed together. The action of delta on my A's is the thing that I'm carrying down through this data structure. Okay, that's a bit of a tangent. I just figured I would go through it a bit. So this scheme is one way to do the thing you mentioned. There's another scheme that we can do, which is a bit better. Yes?
Does this depend on the deltas being a group? Or not?
No, this did not need a group at all. This works on a mock. The next thing is going to need a group. So if I have a group, I can be a little bit smarter. I can say that my lists are actually going to be a pair of a delta and a list. Okay? Now unconst relocates as it pulls out and leaves the delta in place on the list. Okay? But const got trickier. To const A onto a list, this delta will be applied to A, and I don't want it to be. Exactly. So I apply the negation of this delta, so that when it gets relocated by the other thing, it'll relocate. The delta, the list wants to push me 50 characters to the right, so I want to push myself 50 characters back before I put myself into the list, so that when I pull myself out, I'll be pushed out exactly 0 spaces. Right?
Why would you rather do this than the other thing?
Because this is 1 delta. This is 1 delta per list element. This is more memory. Okay?
That depends on the deltas.
This is also the application of the delta to the relocation of the thing, yes. So like that being cheap too. But I'm using this to set up the fact that having a group lets us do more things. Okay? And this is one of the reasons why I have a group. So let's move to the next kind of bit that uses the group structure. Oh, by the way, so I was saying before, like we want lists to be appendable and stuff like that. So Okasaki gives us concatenable queues, or like lists with O1 snock and O1 unconst, like these are queues. If we build them out of the list that we just described, or even I can share 1 delta over this whole like basic thing, I can build real-time queues, I can build real-time concatenable lists, concatenable decks, all this kind of stuff. They're all relocatable at one time. All of them giving me all of the other operations that I want as well. Now I want to do maps. Because I need like mappings from positions to names and names to positions. And here, I want my positions might occur in both my keys or my values. Yeah, both, either and either or both, right? I want to allow for positions to be part of the key, but here's the problem. If I relocate a key, I need to make sure that rel, that little function I have, rel by some delta should be a monotone function. And it should be strictly monotone, so that if x was less than y, and I relocated them both by delta, they should still have the same relative order. Right? So if it's just a position, and I relocate them, they should maintain the same ordering. And that's not unreasonable, I think. And so what I want this for is I want my keys to be able to be positioned such that I can relocate the entire map just by relocating the bin at the root. And then accessing this map node should push the delta down. So I need this notion that rel for some delta is a monotone function in order to make it safe for me to relocate a map without having to worry about keys collapsing or switching orders in the tree or something like that. This gives me the ability to relocate entire maps in a one time. So far so good? But it's still got a problem, maybe not from an asymptotic perspective, but from a constant perspective. So if I'm using these deltas, like I did the first list, where I put the delta in each one of the const cells, there, or here, what's going to happen is this. In order to insert an element, I'm going to burn a path with 0 deltas to wherever I do the insert of the key value pair. And to burn that 0 delta path, I'll have to shove the delta off into the keys and values and into the other branch of the tree on the way down. So what I've done is I've sort of multiplied the cost here by a factor of 4. And I was going to do log work to find the appropriate element. Now I'm doing 4 log n. Now 4 is still a constant, right? The computer scientist, and you can go F. But the actual person who actually cares about how fast this stuff runs, the software engineer, maybe, looks at it and goes, right? We multiplied the cost of every map operation we do by a factor of 4. We made everything needlessly slower. And I say needlessly because if I have a group, I could leave the deltas intact along the path. I walk down with the deltas intact. I want to put a key and a value at this position. I've got a delta that's going to be applied to me whenever I go to access this thing. So I apply the negation of that delta now to the elements I'm putting in. So that whenever I actually finally look up that key value pair, they're shifted back to right where I want them. Okay? So I had to fundamentally use the group structure in order to speed things back up. So I got rid of a factor of 4. Now it wasn't an asymptotic win, but it was a constant factor win of a factor of 4. Now when I start talking about maps, or hash maps, this becomes a bigger deal, because hash maps have lots of siblings. So I'd have to push down to 16 children or 32 children, depending on how wide your hash array map trie is or something like that. So at that point in time, it actually does affect your asymptotics, depending on how you count. But just to be aware that it's actually worth considering where the group helps. And now, here's the other problem. Let's say I have a map that represents all of the stuff I know about one run of text, and another map that represents all the stuff I know about another run of text. And I want to glue these two runs together. This is not just the usual direct product of monoids. It's not just oh, what's the length of this run of text? What's the length of this run of text? Okay, glue them, that's the length of the result run. That part's correct. But when I go to glue the two maps together, I don't just union the two maps. What I really need to do is I need to shift the second map over by the width of the first. I have to relocate the second map. Because its positions are all starting at 0. And they need to be starting by, well, this thing was 50 characters long. I need to start 50 characters, at character 50. So what I want to do here is glue together the sizes. But when I go to glue the maps, relocate the second map by the size of the first region of text. Okay? And in algebra, this is something called the semidirect product of two semigroups. In this case, of a group and something that happens to be a lattice. So this actually happens to be a nice inverse semigroup. It has a nice algebraic structure in its own right.
This is thing, wow, I haven't seen one of these in a long time.
So yes, this is
the semidirect product of groups, yeah.
Yeah, the semidirect product, in this case, a group and a lattice. And this pops up all over the place in any problem where you're starting to deal with serialization or deserialization. Like I have a serializer that's going to write out 50 bytes and another serializer that's going to write out 40 bytes. and you have the length that you're going to write, 40 and 50. And you have the address in memory that you want to write them to. What you want to do is you want to act on the address in memory with the width of the first thing in order to give the address that the second one should be writing to. So Brent Yorgi and maybe a couple other folks wrote a paper on twisted functors or something like that, where they used this notion of semidirect products for applicatives. Here I'm using it sort of like with respect to union. That's not quite the same notion. I wrote another article on how to parse CRCs in parallel. Like how you can glue together, like if I know the width of the text that a CRC goes with, and with the text that another CRC goes with, I can glue the two things together monoidally as well. I can do it with where my CRC is like just like a hash is like a residue modulo prime. I can do the same thing. You just switch out for a Galois field, you get like normal CRCs. If you leave it in just like a prime field, you get that. Both of those things can be parsed in parallel. But what is it here? Right? So here we want the semidirect product of some delta and some other monoid that I'm going to call a relative monoid. And what that is to say, this is a unitary monoidal action. Okay, this rel here had the laws before that relocation by mempty was gained. Here I have a monoid that's acting on a monoid. So I want to have laws for how this thing acts on mempty and the append of two things, not how relocation of the append of two things acts on something. Okay? So here I'm saying is if you relocate by any delta, the empty thing, you get the empty thing. All right? If you relocate unit by delta, you get unit. If you relocate by delta m, and you append that with relocate by delta n, you get the relocation. You could relocate the two pieces independently and glue them together. So you could relocate, you could glue and then relocate, or relocate and glue, and you get the same answer. Okay, that's what I want this thing to be. And under the existence of these laws and this being an action, you know, the delta acts on A, what I can do is I can say this. The unit is semi-zero empty, and append says this: add the deltas, and then the result is take this map and then glue the shifted version of the other map, or whatever A is. So I have M and A over here on this side, and N and D on this side, and I want to shift by M, B, in order to glue them together. Okay? Whee! All right. And then this whole thing itself is relative. So we can now do this for relocating maps from positions to names to positions. Right? Those are things that I could glue instead of like having the thing that I'm using that recognizes a single line produce just the DIG language structure. It can also build a map from positions to names and a map from names to positions. Okay? And then I can glue those together across multiple lines. Yes?
Are those laws correct?
I hope so.
The second one seems weird, like for semi, like you would be shifting the second thing by 2D in the second on the right hand and 1D on the first.
Wait, where? Which law? Or
Because
which?
if you push D into M and then
Oh, this guy down here?
The law that you have on the top, I think, was talking about.
yeah,
It's the second
the
one.
comment.
This should be correct. This is straight up out of the definition
Okay.
of what it means to have a unitary semigroup action on a semigroup,
Okay.
or a monoidal action on a monoid.
Which of the things in this slide is supposed to be an instance of relative monoid, I think, maybe is the question.
This needed, where I wrote monoid semi-A, this needs relative monoid A.
Okay.
Yes, that is the bug in the slide.
But semi itself is also a relative monoid?
Semi itself is relative. I don't know if it's a relative monoid. I don't know that I've ever actually checked.
Oh, it's a monoid and relative.
It's a monoid and relative. I don't know that it's a relative monoid. Check. Relocate my empty
I think
is not empty. No, it is not.
Okay.
This is not a relative, semi itself is not a relative monoid, it is relative and a monoid.
That's why I was confused. I thought that was.
Is that what you meant?
Yeah.
Okay, yeah, because that won't be, this will not be, like, if I relocate my delta, this will be semi-D map D.
Right, yeah.
And I have a file that has all the crazy proofs.
Where'd you prove it in?
By hand in Haskell.
Oh.
Just like, you know, me spending the flight.
Yeah. This morning came down in a fire.
Oh, which one? Oh yeah, the no redundant constraints like warning. I hate that warning with a passion. It's like, oh, you run a class that just has a law in it. No. But yeah, like this has a whole pile of.
Okay, I believe you.
It just goes and goes and goes and goes and goes to prove it by cases that these, like, you know, build an ordered semigroup for semi. Anyways. So anyways, this part's easy because it's not claiming to be a relative monoid itself.
Okay.
So what I want to do is I want to deal with how do I do a name capture. I want to I almost want to say I want like a syntactic notion of name capture, but it's not even syntactic because whenever like a computer scientist talks about syntax, they pretty much always presuppose that they're able to build a syntax tree, right? They've already gone from somewhere from source to get to syntax, and then they start moving on to assigning semantics, right? But like, you know, if you look at I want to work left of syntax at a source level. I haven't even built valid syntax trees yet, and I still want a notion of name capture that if I had a valid syntax tree that I could construct would be the correct notion of name capture, but which does something sensible even in the presence of garbage. Okay? So what I want to do is I want to make some observations about names at a source level, not at a syntax level. Okay? In every language I actually care about, the names are brought into scope. There's a vacuous statement that I can make, which is that names are brought into scope for a finite number of subintervals of my source file. Okay, now it's a vacuous statement. There are only a finitely many number of intervals in my source file. I don't have infinite source files, so congratulations, that's true. Okay? But the non-trivial component is the fact that these intervals never partially overlap. There's never anything that brings into a scope a name from characters 0 to 50, and another thing that brings into a scope a name from characters 30 to 1,000. Right? Where there's this window in the middle. Okay? These intervals either nest like Russian dolls, or they're disjoint. Right? I can know which interval is the nearest containing interval at any given moment in time. Okay, allowing for equality. And so as a result of that, if I have the interval map and I have the occurrence of a name, look for the nearest containing interval for that name, and that is the binding site. Or that tells me the binding site that this is referring to. Okay? So this is a source level version of name capture based on this notion of these intervals that do not partially overlap. If they ever partially overlap, then which was the nearest containing interval wouldn't be well defined. But since we have this property, we're good. And again, we can relocate entire interval maps at one time. So I can build these things up as I'm gluing my lines together. All I need to know is some quotient of my language that describes what my binding sites look like. So I have to commit to more syntax. Right? This is like my ever slowly like reverse engineering of a language continues, right? So what is the next bit of syntax? Well, declarations, foo bar baz equals, lambdas, right? So what I can do here is I can say, well, what is the scope in which append is being, or let's say parse is being brought? Parse is brought into scope for the entire file. It's a declaration. But its arguments, say this with x, x would be in scope just for the current statement. Like the interval, you can look at the interval that's coming out of each one of those things. One is the interval of the whole source file, one of them is just the interval of the current line. Okay. Similarly here, append is being brought into scope technically for the whole source file because this is funny. But the A, B, C, and D are only being brought into scope for the current declaration. Where clauses get brought into scope. The things being bound in the where clause get bound in the where clause, the other statements of the where clause, and in the body of the where. Let, the body of the let, and the in, you can work through where the intervals go. It's nice because I don't have to actually think about, like, my parser just spews text into the thing. It doesn't think about binding sites. It doesn't get substituted in, like, bound or any of those kind of things. It just gets grabbed out of the interval map later on. So this gives us name capture. And now we have enough to support the renamer if we're careful. Like if we build a couple of maps, one map where I delete all the occurrences of a name whenever I capture, and the other one where I don't, then I can do things like determine when I have foobarb as equals, like if I renamed this, if I renamed this to bar, this would cause problems because this would become a capture. Right, so I need to be able to figure out where names could potentially become shadowed. And so you need two maps in order to calculate it. But with those results, I can actually give you, hey, look, will this renaming succeed without changing semantics? And the nice thing about it is, it would do something sensible even if you had that. Which is kind of cool to me. So I wanted to do the right thing on a well-formed syntax tree and do a sensible thing on garbage. It's sort of the mindset that I've had.
So you can call it a recycling plant.
Yeah.
If you have like Haskell with scope type vars, then you can
Scope type variables screw all of this up.
Okay.
So fine, I'm an independently typed language with one scope. Scope type variables make it unclear which one is the binding set, right?
Or in general, anything on the right of a colon if you have a binding with a type annotation, right?
Yes, because you don't know. Well, you don't know if those things are like. I guess scope type variables don't really screw you up as badly as it seems at first. Scope type variables seem to make it so that it's unclear which ones are the binding sites, but Haskell requires you to use an explicit for all keyword to tell you where those binding sites are, so it actually recovers. If you wanted sort of implicit scope type variables, if you just said, hey, look, the scope type variable rule is always on, and any occurrence of A inside of a term that's got a type signature on it is referencing to the outer A, then you would have the problem. So, the other one is languages that have multiple contexts, like a type context and a term context, where you have different term variables and type variables. Then which ones refer to which, you have to, like, it's a little bit messier because now you have to figure out whether the moment you cross the colon, you're in a type-like context, and you need to keep track of which kind of context you're in to know which way the names collapse. So, so there's fiddly bits there, and it gets messier. Like I'm like, oh well, I'll just do this in an independently type setting, but then you have problems like. You have this kind of crap, right? And then this thing is a binding or not, is it a type signature? Like it's, the choice of syntax used there is also a damn mess. So I'm still working on some details when it comes to picking a nice language. But I do like the notion that I can get sort of like hover over this will give me the type signature, like if I had explicitly written a type signature down here. If I hovered over balanced somewhere else in the file, even if it was garbage between me and it, I would actually get the highlighting. I like that. That appeals to me. That layout acts as a strong error recovery point. If we've tweaked the layout just enough that it's not so brittle. So what did we have to do? We had to change layout because if we didn't change layout was too brittle, and so we couldn't use it as a strong guarantee about where you could resume. right? So you had to still parse layout from left to right. But now that we've changed layout can be parsed monoidally, just like my parens. We had to change comments. We got rid of multi-line comments because they were brittle. They required me to parse left to right through my file. I didn't want to pay that. And again, I could do that. Like, if to support an existing language that already has those features, fine. You just accept the fact that you do some sort of linear pass, scrub out all your comments, take your positions, and then move into the next pass. You just give up on the dream of having that sort of nice polylog-ish time. And unfortunately, you kind of have to give up on the dream the moment you add multiple kinds of brackets and braces here, because as I go to pair these things off, I have to pair them off one by one. So unless I play some crazy games to try and make it so I can compare arbitrary sequences of closing and opening contexts in constant time, I can't have it anyways. So it's not, I can't quite get the polylog back.
What if you assume it's perfect?
Hmm?
What if you assume the input file is perfect?
If you assume the input file is perfect,
Wouldn't you be able to do it?
oh yeah. But most of the time it's not going to be while the user is editing. So my goal is to support things robustly even in the pathological as you screw things up case. Now I'm willing to have...
While edited.
While editing, yeah.
Basically, yeah.
And again, like, should you immediately highlight to the user all their stuff in red the moment they type opening brace? Maybe not. Maybe you should delay a little while. Maybe you should have the editor automatically insert the corresponding pair to minimize the perceived breakage, right? Maybe you should delay a second or two before you type check. But having the option to do it immediately is to me, interesting, right? The other thing is the result of producing that map and then removing the thing gives me all the free variables, which are all the things I should be looking up in the other modules that are in my dependencies. I can go quickly find those things in the spine without actually fully parsing the file. Yes?
I mean, I get the desire to be able to want to reason about the source files incredibly fast, but how big of programs are we talking about? You're not going to really see the difference.
Are you? I don't know. I find that if I use GHC IDE, like for Haskell and stuff like that, on a small-ish code base, like that 5 seconds or so is an eternity to me.
But you're only parsing one source file at a time. You're not parsing the entire code base.
Maybe.
And I mean, good design.
GHC IDE doesn't do that. Isn't that smart, right? And the other thing is that stuff that depends on me gets broken as well. So it does kind of transit. Like if you want to, like, who do I break by making this change is another consequence, not just the source file. So you want to be able to do the equivalent of a full build to really get like both sides of that coin. Otherwise, you just see the and then all your consumers get broken silently. So this is the. So I have this code on GitHub as GitHub Kmett Coda. I think there's actually a slide here that has references and stuff. And it has, so this is the actual code. It's we can actually see the data.map has been ripped out, dropped in, with delta shoved in. All the horrible code. Oh, it gets horrible too, because like in order to do rebalancing, I want to leave the deltas in place. And so I have to recalculate, oh, like, well, this is the sum of the deltas, but I have to subtract off this delta. And then it's just, Yeah, so my brain exploded all over the keyboard here. And it produced this code. And I built type check, so go me. I managed to, because I didn't trust myself after that. I went and wrote like a bunch of unit tests and stuff like that sit there and built like a model of things I might do with maps, and then built an implementation of it that used my map and one that uses the real maps and then laboriously pulls everything out, relocates them, and puts them back into a new map. To make sure that the results compute the same thing and stuff like that. I did the same thing for the relative list and all this kind of stuff. So I at least have like quick check level sanity. Okay, so yeah. Not so great, but it at least let me have some kind of assurance that it wasn't doing stupid things. It found a bunch of stupid errors early on, so. So if somebody else wants to go off and like prove this stuff in Coq or Agda, knock yourself out.
I wonder whether liquid Haskell would be good enough.
Maybe. I don't know enough liquid Haskell to do it. You just have to lift too much stuff, I think, into the liquid Haskell engine. Yeah, so I've got that stuff. I've got, oh, here, let's,
Do you have a demo of like showing?
I was meaning to do that before I did the talk at Scala World, and unfortunately, I didn't get it done for them, and I haven't gotten it done for you. I do have, at least the language parsing stuff is all in now. So this is the actual version of the code that does all that opening and closing context stuff. So we have a located, whatever the pairing type is, and a cat level sequence of whatever your token type is. And then, so here's the horrible thing for the language context. It's a cat level sequence of closing context, followed by a sequence of tokens, followed by a reverse cat level sequence. So this is, I can unsnock, but not unconst. Okay? So I can pull off on the right-hand side, not on the left, of opening context. So I need to pair the right-hand side of these with the left-hand side of these. So I only have efficient access to one end of the structure. But I can append in O1. And their constant factors are good. Then a closing sequence of tokens, just because it's cheaper for me to bolt onto this token than it is for me to unsnock, fiddle with it, and then put it back in. And then I need to know the last token I put in, and it's the only thing I ever need when I start doing the layout stuff, because I need to know, was the last thing you saw a where, a do, an of, a let? Like I need to know if it's a layout introducing keyword. And so I have this one little thing that I have to supply that is just sort of just a little bit of information about the last token. Because I need that in order to make the layout, the little V-shaped thing that I was showing before, go. And the monoid for this is a little, yeah, it doesn't work at this resolution. It doesn't work in normal resolution, but it works even less here. It's just a dozen type parameters go. As we peel off opening, closing pairs, if they match up, then they cancel and form a rich nested token, and yeah. Otherwise, they form a mismatched token. Otherwise, we overflow in either direction, or we're done. Yeah. So this is the kind of stuff that goes on behind the scenes. I tried to make this generic in the token type so I could reuse it, because God knows I don't want to write that code again. And then I have a Haskell lexer that's actually built with Alex. That spits out, basically legal Haskell identifiers and stuff. It's just the only thing that's missing from here are the normal comments. It handles standard Haskell grammar otherwise. And it builds my own token type, whatever it is. Like this is a token and it has deltas in it. And I have this notion of a rich token elsewhere, which supports all the nesting and stuff like that. So I just embed rich tokens into my token type and move back and forth. So that lets me support the nested cases and mismatch parens and all the warnings and errors and stuff that I needed for the back language stuff. But this is the peculiarities of my Haskell-like syntax. Hey, look, this is a token for something I haven't yet given an interpretation to. Here's a keyword. You've parsed a literal integer or a double or a string or char, right? And so this is the set of tokens that come out of this thing. They're tokens that come out of here, and occasionally you'll get like a token rich of a nested paren with the machinery for that. And they have deltas in them, so these things, if you relocate the tokens, you relocate the whole token, and all of the stuff underneath it, no one knows. It uses the same trick that we've been using over and over and over again. If you take nothing else away from this talk, this notion of actions and pushing them down through structures slowly, I think is kind of a useful recurring pattern. But yeah, this is just basically an unmodified Alex Lexer. I mean, it's modified a little bit because it works over data.txt. So I had to build some code to support that. But and this lets me parse directly into such a syntax tree. And then I have a bunch of stuff for building up ropes as finger trees of lines of text that produce the Dyke language machinery for each of the lines and the delta associated with that thing. And I build another monoid that summarizes over those, which folds up using the layout stuff. And so the result here is, the nice thing about it is the layout keyword tells you which parser to use for the stuff underneath that layout keyword. It almost tells you. I'm lying a little bit here. So if I encounter the word where, I know that these are going to be a bunch of statements. Okay? If I encounter a do, I know that I'm going to get a bunch of monadic binding things. If I encounter a let, I know I get a bunch of statements again. If I encounter an of, I know I'm going to have a bunch of case alternatives. Okay, so each one of those four things told me what I'm going to see next. Okay? Now, the reason I said that I'm kind of lying is because where doesn't tell me that I'm going to see a bunch of statements next. Because where gets used overloaded in umpteen different ways in Haskell. We can care about module something where. And now we can have data type declarations inside of here. Right? But it's not valid for me to have data declarations inside of, I don't know, inside of a where block for a function. Or where for a case statement. Right? So I need to know what the where is associated with. Instance something where. Class, each one of these means something a little bit different, which is just annoying. Type instance, or type, what is it?
What's your own language? Make it module where, instance where, class where, type where.
Yeah, well, I mean, the thing here is, what I need to know is I need to know the first token and the last token in the thing that introduces me. And that's okay, because I have cheap access, O1 access to this end of this thing. So that was the only wibble that I have. And most of the type family stuff is becoming pi, just fiddling with, yeah, screw it, and the types. Okay, so that's the state of things at this point. I've got a bunch of random modules. So we have, I mentioned before, this notion of semigroups with zero. Like where there's a, there's a zero element that 0 times a is 0. Like it cancels everything. Like the prefix type that I had was semigroup with 0. I have a little REPL that doesn't do much yet. I have my own copy of data.figure tree that fits with the rest of the machinery here a little better. Relative thing that carries around its own position. It ignores it.
Relative.absolute.
Yes. Damn it! It's in that position. It doesn't listen to you. Anyways, I got a whole sequence of things that are relative, the relative class itself, the delta data type, and a bunch of classes for talking about deltas that have some non-trivial interactions with the way the bunch of classes that talk about relative work, relative lists, the queue stuff that I talked about earlier, where we're building the server stuff is talking to the Visual Studio Code using the language server protocol. So like some of my positions correspond to some of my new positions correspond to some of my old positions and vice versa. And moving back and forth is kind of fun. So I built a bunch of machinery for doing that. The document stuff is a rope worth of these crazy monoids, the language stuff that we've talked about, my keywords, the lexer we just saw was trying to get Alex to do lexing inside of this crazy thing. Names, prefixes at us, semi-lattice, the rich text token support, ropes. Yeah. And then the actual bits for the language server protocol and stuff are packaged up off to the side in such a way that they'll probably wind up becoming a separate package, to be honest. They'll probably just be a little LSP package, yeah, assuming the name hasn't been taken sometime relatively soon, that just has the machinery for talking to the language server protocol. So if you want to build your own language and you don't want all this crazy stuff, you can just, yes, you can just steal those bits. So that's the status of my little toy. I can launch Visual Studio Code probably, but it's not going to do anything interesting. Yeah, I can't even launch it. So I don't know. I haven't tested it since the last time I built like a week ago. So, all right, that's all I got. Any other questions?
Do you happen to know whether there are any maybe existing either programming languages or data description languages that were designed with fast or easy parsing?
Were there any existing data description languages that I defined with exact fast, easy parsing in mind? No. Sort of. There's the closest thing to a general purpose tool that kind of fits into this, like that can handle a real class of languages that I know of is Valiant parsing. So Jean-Philippe Bernardi and Cohen Clayson wrote a paper on Valiant parsing a few years ago, not too long ago. And Valiant parsing is like if you know like CYK parsing or chart parsing in general. You can kind of squint at this as the diagonal is where your tokens are, your individual characters are, and then above the diagonal, like a parse from like at this position is a parse that starts at this position and ends at that position, right? It's like the top of a little wedge in a little diagram of like, oh, here's a subject-verb pair, and you start building up your grammar. Until you fold to the root, you try and find a parse that is a parse in the upper right-hand corner, right? Okay, and so in a CYK parser, you do this exact same construction, but you do n cubed time, guaranteed, because you pay for everything. The thing is, like, this is for an actual C source file. You can see how sparse it is. So having a fancier sparse technique that can take advantage of sparse matrix multiplication pays off a lot. Okay, and so CYK parsing, if you use Valiant parsing instead, you can parse an arbitrary context-free grammar in n2 to the whatever matrix multiplication time, right? It's a number, it keeps getting done. It's 2.373 now. No one's ever going to parse in that time because, hey, the constants are enormous. But this is sort of the most general tool for doing this that I know that works for a real class of language, like context-free grammars, right? I'm not even trying to do a real class of language. I'm going to do, I'm going to respect this, I'm going to respect that. I'm taking all these arbitrary choices to narrow my problem down to make it come down from here to like n or n log n, right? So in practices like n log squared n, they actually include an extra log factor they don't need to in the paper. So they said it was n log cubed n for real languages. And it's bad for languages that involve lots of parentheses. Not that we know how to handle that or anything. You can improve the constants by like if you, instead of like parsing for individual characters here, if you had some kind of monoidal lexer, like a normal, or more or less a normal lex style lexer, where you put in just the little sparse parses for, hey, look, starting at this position and ending at this position is an identifier, right? So this becomes much sparser here, and then these constant factors become much, much nicer. So I've been kind of, like, this was the thing that I was playing with as my, like, if I had to do this for real, right? And I couldn't get away from the nested multi-line comment thing, and all that kind of stuff. This would be the tool that I would drag out because it can solve it. And it's kind of log cubed-ish in practice to do reparses. So like if I made small edits here, I could build this thing into a finger tree and then glue the finger tree back together. So they've got a modified form of BNFC, which is why I mentioned it, because you have a tooling question. So they have a modified form of BNFC, which is a tooling thing for parsing arbitrary kind of tree grammars. And I think like the cubicle type theory folks use it. The cubicle TT implementation actually uses BNFC. I don't think they use the Valiant parser or any of that kind of crap, but they at least use that same tool to specify the language. So that's at least close thing I can answer. But
People use anything else right now for incremental parsing?
people use anything else for incremental parsing?
Because I assume that that's kind of like the main reason for doing this is so if someone changes one line of the file.
Yeah,
it goes-
they might put checkpoints in typically. Like I don't know, like you the first 4K at this point. Like I got the state of the parser or something like that. If I have a purely functional parser, maybe I can just grab the whole state of the parser.
Okay,
But that just gives you a resumption.
yeah.
So I got nothing past that.
Okay.
But now this is like there was a talk by Anders Hosberg on modern compiler construction, and he basically talked about, hey, look, if you're building a modern compiler, you really kind of turn everything inside out, and whenever the world changes, you just throw in the world, and you try and make sure that you can do your type checking kind of inside out. Like, I want to ask about this particular type, and you look around you to try and get the information, rather than build it as a monolithic pass that computes that one thing. And I thought it was kind of a neat talk, but it didn't. It was like, yeah, we really can't reuse any of the previous state. We kind of throw it all away. Like they cache some of it off to the side. And I was like, well, what happens if? What if I was willing to throw, all of Okazaki at the problem all the time, right? And say, hey, look, I am willing to store this stuff internally, and I'm willing to think very carefully about using laziness and how it stages everything through. Is it possible to build stuff? Well, the answer is yes, it seems like it's possible to build it. It doesn't look like it's building fast, I'll give you that. The code runs fast, but writing it is slow. So maybe he does have a point. I will concede to the sort of master of compiler design there, that he's been doing this a little longer than I have. So.